Hello, everybody. Welcome to the webinar on circuit breaker testing. I hope you are all good. I see we have a very nice attendance. And today, Mr. Simone Meneghin will be talking about, as mentioned before, circuit breaker testing. Simone has been with ISA now for more than 8 years. He studied electrical engineering and he has not a bachelor's but a master's degree in electrical engineering. For a long time he's been an engineer in commissioning engineer, after which he moved to ISA, where he fulfilled the duty of product manager, or to be more exact, application specialist. He was a part of many teams, out of which some of the latest devices were created, and CBA 3000 was also one of his, let's say, brainchilds. So I think we have the best possible person today to show us what we don't know and what we do know. So without any further ado, I give you Simone Meneghin. Simone, the screen is yours.
Okay, thanks, Andrei. Hello, everyone. Let's start to discuss together about the testing of circuit breaker with special attention on high voltage circuit breaker. Let's start to say, what is a circuit breaker? It is an automatically operated electrical device designed to close or open contacts inside the chambers, thus closing and opening an electrical circuit under load or fault conditions. It is very important that when there is a fault in the line, it operates with the fastest possible time in order to clear the fault in the fastest possible time. The device that in substation send the command to open to the circuit breaker is called the protection relay. It takes from the voltage and the current transformer the measurement of current and voltage, and is able to recognize if something is going wrong. And if something is going wrong, that means there is a fault in the line. It issue an open command, and then the circuit breaker open the main contacts. Then the fault current is interrupted. So when the circuit breaker is closed, imagine two pieces of metals that touch each other, and then the current can flow into these two. Let me take the pointer, please. Yes. So imagine two pieces of metals that touch each other. Then the current is allowed to flow in those two pieces of metals. The only way to interrupt the current is to separate those two pieces of metals. And when you do this operation, in the very beginning, the current still flow through the air, and this is called electrical arc. And this condition must remain the last, the less possible time, because this is a condition that is dangerous for the metal. Once the two metals, the two pieces of conductors, are well separated, then the current flow is actually interrupted, so there is no flow anymore. Why the electrical arc is so dangerous? Because it may damage the surface of the contacts, reducing a lot their conductivity. Imagine a welder. This is exactly what happened. If you apply a differential of potential between two conductors, then you create this arc, and if the energy is high enough, then you will fall in this situation. And you can see that this cannot be maintained for a long time. Otherwise, you are really destroying the main contact of the breaker. Must be understood that not all the arcs are so dangerous for the breaker. The circuit breaker is designed to open hundreds of times the level of current that falls in this range. between 100 and 300 amps. This is the typical load current for a high voltage circuit breaker. So you can see the main contact is designed to withstand hundreds of these kind of operations. But when there is a fault, the level of the current becomes very high, let's say higher than 1 kiloamp. So the arc that will appear between the two pieces of metals is so strong that it from time to time damage a little bit the surface. This means that the circuit breaker cannot open so many times the fault current. We can conclude that the fault current interruptions reduce significantly the remaining life of the circuit breaker. There are solutions to try to keep safe the circuit breaker as much as possible. Inside the breaker, you can see there are the main contact and also a so-called arcing contact. This is another piece of metal that is there to absorb the energy of the arc. It is composed by a contact with a little bit higher resistance than the main one. So the main contact is in the range of microohms, where the arcing contact is some milliohms, and it remains connected for very few milliseconds during the switching operation. Each time the CB interrupts the fault current, part of the arcing contact burns. So it is required to measure its equivalent length, but this will be explained later on. Another way to reduce the impact of the electrical arc inside the chamber is to place into the chamber a compressed gas, not any gas, but a particular one. It's called SF6. That is a not flammable, not poisonous, and odorless gas that act as an interrupting medium and also an insulating medium. The power of this gas is proportional to the pressure. So higher is the pressure, greater is the interrupting power. It's very important to keep control of the pressure inside the chamber, because if the pressure reduces and it becomes too low, the CB cannot operate and must be put out of service, and then a refill of the gas must be done. There is not only one model, not only one type of breaker. There are several breakers. We can see 3 pictures here. There is a 1 break per phase, 2 break per phase, and also 4 break per phase. The number of breaks increases as the nominal voltage increases. So we can see that above 230 kilovolt, we start to see 2 break per phase. This is necessary to increase the separation between the two pieces of metals. If you remember, the distance, higher is the distance, less is the possibility to have an arc. Higher is the voltage, also this distance must be higher. Otherwise, you cannot actually interrupt the fault current when you open the main contact. In parallel to the main contact, you can find some devices that are there to control, to keep under control the voltage on the breaker, on the main contact itself, because also an extra voltage can be dangerous for the breaker. One solution is to place capacitors, so-called grading capacitors, that are there to keep balanced and equally distributed the voltage across the main contact during switching operations. Another device that you can find is the so-called pre-insertion resistor, that is there also to reduce voltage transients transient generated when a no load transmission line is energized and then re-energized after a line fault. Gradient capacitors and pre-insertion resistors can be both present in the same time. Why the voltage transients are dangerous? Because they have voltage peaks whose value can go beyond the rated voltage. And if you go beyond the rated voltage, then the circuit breaker is not designed to withstand, then you can damage. Okay, this is Albert Einstein. I suppose you know him. From time to time, he will pop up in our slides, helping us to highlight some few concepts to better understand why we mention some concepts to explain our webinar. In this case, he's telling us from where extra voltages comes, because you have to see the line is not a pure resistor. Actually, is an inductor, mainly an inductor. So every time you apply and remove voltage, so you're going to stimulate a reactive component, then it reacts. In this case, increasing a lot the voltage. But we have to say that nowadays, new circuit breaker do not use gradient capacitors and pre-insertion resistors, because the design has improved and they are not necessary anymore. So when you see gradient capacitors and pre-insertion resistors, maybe you are in front of a quite old circuit breaker. But not only high voltage, also medium voltage circuit breaker can be tested in the same time as an high voltage circuit breaker. So most of the principles and concepts remain valid for medium voltage switch gears. These devices are designed to operate at lower voltage, but basically they do the same job as the high voltage breakers. Now we go a little bit more inside the so-called operating chain. So when there is the necessity to open a circuit breaker, what actually happens in the circuit breaker? First of all, you need a coil command. So in the device that once energized will trigger a spring. The spring release the energy to some mechanism and leverages, and this mechanism and leverages transfer the movement to the main contacts. After that, we have also to remember that I cannot be informed about the main contact if I don't use some auxiliary contacts that repeat the status of the main contact, because I cannot have a look inside to the main contact. I have no possibility to understand unless there is a device that is repeating that information. This is not less important, because this information is used from devices in substations, such the relays or SCADA. If the relay, for example, after the relay wants to open and is not receiving back the information that the circuit breaker actually is really open, then it can decide to activate a logic called breaker failure. The breaker failure logic typically open all the breakers that are connected to the same bus bar. So it's very important to control that the auxiliary contacts are well working. The energy comes from a motor. So we cannot forget that there is an electrical motor that charges a spring. Otherwise, the energy cannot be stored. So we need also a motor. This is one example for a one break per phase circuit breaker. This is an example of a real results. So we have now to be start to be familiar with this kind of graph. In the top part, you see this digital graphs. The thick line represent a close contact. A thin line represent an open contact. The black in this scheme, the black contacts are the main contacts, and the red one are the auxiliary contact. And this graph represent the coil current that is flowing in it when it is energized. We can see that after few milliseconds, the main contact, more or less 18 milliseconds, the main contact are open. So this gives you an idea on how fast the circuit breaker must be. Here there are two auxiliary contacts, one that inform the substation about the open position of the main contacts, and the other one inform about the closed position. You can see that the auxiliary contact that inform about the open position become closed when the circuit breaker is open, and vice versa. The auxiliary contact of the closed position become open when the main contact is open. This is a typical way to use the auxiliary contact. So when it is closed, is a confirmation about that status. So auxiliary contact that must inform the substation about an open position, it becomes closed when the breaker is open. That's why this auxiliary contact is closed when the main contact is closed. This table is helping us to summarize what are the elements that are composing the circuit breaker and what are the parameters that must be kept under control one by one. So coil commands, I need to measure the current that is flowing in the coil command, and in this coil current I need to check what is the peak, what is the flowing time, and also the shape. Main contacts, I need to verify the opening and closing time, the static resistance of the contact, and also the dynamic resistance in order to understand the condition of the arcing contact. Now, when it comes to auxiliary contact, what we have to do is just verify the switching time. Pre-insertion resistor, I need to verify if the value is still inside the ranges that the manufacturer suggests, and also the insertion time, because as the name suggests, it is also a moving part that moves more or less together with the main contact, and the insertion time is a time that must be verified. When it comes to the mechanisms and leverages, we have to check if their movement is okay, and also correlated to the movement, we have to verify the speed, because the speed of the leverages is the parameter that make fast or slow the open time and closing time of the main contact. When it comes to motor, what we have to check is the operating current. So if the current that is used by the motor to charge the spring is correct. In order to do proper test, you need also a proper tool. We, as Altanova, we can suggest the so-called CBA 3000 is our latest designed circuit breaker analyzer that is able to perform all the tests that we mentioned before. Is a device with a built-in computer, so you don't need a laptop to operate. There is a section dedicated for the time measurement, and is this one. You can connect up to 24, can be main contact and also auxiliary contacts, up to 6 coil command, and you have analog inputs for any analog measurements, such as voltage from the motor, voltage from a current clamp, and also voltage that comes from a micrometer. Here we have the micrometers. So these are 3 generators, 3 DC current generators, because we will see later that will be necessary to measure the resistance of the main contact. Now we discuss about coil commands and what are the information that we can get from the shape of the coil current.
So, Simone, if I could just add one thing, maybe now we could launch one of the poles.
Yes,
just to see.
You're right.
And I can launch the poll, but I would like to turn your attention. We have one interesting question from Mr. Reimert. I don't know if you can see it. It's the only one unanswered. How to eliminate or suppress the voltage spike when closing a circuit breaker?
Is the pre-insertion resistor. Is the also the name suggests when you close, so before the main contact touch each other, the pre-insertion resistor is there to absorb the energy.
Okay, thank you. So if it's okay, I'm going to launch the poll right now.
Yes.
Right now, the question is, the main contact is designed to withstand how many normal and how many fault interruptions? So answer A is hundreds of normal and hundreds of interruptions of fault current. Answer B is hundreds of normal and only few interruptions of fault current. And answer C is only few normal and few interruptions of fault current. So I see that the answers are a little bit, yes, they're good. Yeah, we have 25–30% people voting, and with more than 300 attendees, that's quite good. So feel free to vote. And in the meantime, I saw many people raising hands. So please, I think it would be better if you want to say something to us, ask a question, or you put your comment in the chat. That would be the best thing, because right now we cannot handle raising hands. 45% of people have voted, and I see 65 people have the correct answer. Come on, let's have 15 more seconds to have at least 55% of people voting. And 66 people have the correct answer, which is quite good. 67. Okay, I think I can say in 5 seconds we close the polls. 4, 3, 2, 1, and we close the poll. 63% of people have voted, and 66%, the correct answer is hundreds of normal and only few interruptions of fault current, which is answer B, and 66% of the people got that correct. So 27 had answer A, 7% had the answer C. So thank you, you've been watching attentively, and now Simone can proceed.
Okay, thanks, Andrei.
Okay.
This is the typical shape that you can get after a normal operation. Can be either an open or closed operation. So the first part is the first energization of the coil, where the plunger is actuated and the main contact starts to move. But when the plunger strikes the latch, the main contact continue the movement, you can see a drop in the current. This is telling you that more force is required in the breaker, so there is a drop in the current. So this is an indication that something is applying effort to do something. After that, the current continue and reach the peak. The peak is only limited by the resistance of the coil itself. Of course, thanks to the Ohm's law, it depends also from the supply voltage. But the variation of this peak will suggest that there is a variation of the resistance of the coil. So typically the resistance of the coil can increase because it starts to become old, and if it is less conductive, then this can create a problem. So if the resistance increases, then the current will not be enough for the correct operation of the breaker. In this position of the shape, you start to see that the current is falling down. Means that in this point, the main contact reached the final position, and then the coil command can be de-energized. So with a breaker analyzer, you can measure the flow time and also the peak voltage. This analysis on the shape is more for human operators, because what you have to do is to compare one graph with another one in order to understand if there is a difference. Maybe plunger and latch are two words that do not tell you so much. So I try to put an example. Imagine that the plunger is the arm of the boxer that transfer the movement and the energy to the main contact, but it cannot move everywhere. There is a latch that stops the movement, and once the plunger strikes the latch, then you can see this drop in the shape, in the current in this position. So analyzing the shape of the coil is possible to get information about plunger and also latch. As you probably already understood, what you have to do is to compare a reference shape with another shape that can be different. In case it is different, maybe it's because there is a defect in the plunge or in the latch. How to measure? You have to connect the open coil or the closed coil to a device that is able to read the voltage and also measure the flowing current. With our device, is possible. So you can connect up to 3 open coil, 1 closed coil, but also 3 open coils and 3 closed coils. Now we go to discuss about the main breaker contacts and how to measure the opening and closing time. As we said before, especially the opening time is the most important parameter. So the normal way to understand if the main contact is open or closed is to measure a resistance value. You can imagine when the breaker is closed, you expect a value of resistance, typically a very small value. And when the main contact open, then you find an open circuit. This means that the equivalent resistance is equal to infinity. So we need a device that is able to to measure resistance and understand and discriminate what is a short circuit from what is an open circuit. And if we plot this over the time, we can see that when the resistance is not infinity, we can say that the CB is closed, and when it comes to be infinity, then the CB is open. So we have to find a threshold because we are talking about devices, automatic devices that must take a decision. So somewhere we must place a threshold. So when we pass through this threshold, we decide that the circuit breaker is open. Let's say that this value is 10 ohm, and this value is a typical threshold of the traditional breaker analyzer. These are schemes that tells you how it's possible to connect our device to the main contact. So just to take two wires and connect this plug to this position and this plug to this position. This is a 1 break per phase. This is a 2 break per phase. So the number of wires that are necessary is 3. One is the common between the two breaks, and then one wire for the break number 1 and the second wire for the break number 2. We have to do not forget that we also need to send a command, because if I want to open or close a breaker, then I have to energize a coil. So I also need to connect the coil command. I'm not repeating here the schemes because it was already mentioned before. This is a real picture from the field. Give you an idea on what you need when you are in the field. So typically you need a ladder, because when you have to connect a clamp on top of the breaker, then you cannot go without a ladder or an elevator. And this is a table, more or less is a table where the breaker analyzer is placed. With this zoom, we can see better what we saw before in the scheme. Here is the cables, and this is another zoom to better understand what is the final configuration of the connection here on the breaker analyzer. Must be noted that every input has one LED that tells you in real time the status of the main contact. So the green LED means that the contact is open. If it becomes to be red, it means that it's closed. These are other examples. We can see now the close operation and the open operation, and we see the behavior of the three main contacts. And starting from the moment when the current start to flow, that is where also the timer start to count, we see from here to here, phase B, this is the time, this is the closing time for the phase B, and from here to here is the closing time for the other two phases, A and C. The same concept is applied to the opening operation. So the timer starts from the moment where the current starts to flow and stops when the main contact changes status. You can see that the three poles are not exactly moving, completing the movement in the same millisecond. This is quite normal, and this is a time difference that can be measured, and why not keep under control, because this so-called pole spread must remain within a certain range. The operations sometimes does not come alone. I mean, you just not open or close. Sometimes you need to implement some cycles. The most typical is so-called reclosing cycle. But why they are necessary? So most of the fault in the transmission or distribution line have causes that disappear immediately after they occur. The thunderbolts are an example. So thunderbolt comes and 1 millisecond later disappears. So based on this assumption, after the circuit breaker open, why not try to reclose in order to reduce the time for the line to be de-energized? And we know that if a line is de-energized, this creates a problem in the network. So if there is no reason to keep open the transmission or distribution line, one tentative to close is necessary to be done. But there is also the opposite situation. The fault is permanent. And for instance, trees that grows under and below the line is an example. In case like this, if there is a fault and you open the breaker and then you close because one tentative must be done and the fault is still there, immediately after a further open command must be issued. The standard way to indicate in the nameplate of the circuit breaker how it must behave during an operating sequence like this is indicated in this way. So we have now to be familiar with this indication. So O-T-CO. So the reclosing cycle is an open command, then a time delay, and then a close command. This is a reclosing cycle. But after you close, you need to open immediately after because the fault is present, still present. This take the name of switch on to fault. The time delay between the first open command and the first close command, so the duration of this that time change the name of the reclosing cycle. So if it is 300 milliseconds, we can say that is a fast recloser. But if it is higher than 30 seconds, we are discussing about slow reclosers. The complete sequence, reclosing cycle, in particular the fast recloser plus the switch on to fault is the most critical sequence, because the springs must release all their energy in a very short time. And if you see here, it's not trivial, because look, the mass of the circuit breaker is 7 tons. So you can imagine how heavy can be the main contact, and thinking that we have to move a so big mass in a very short time, you can imagine how much energy is required. And that's why it's the most critical sequence when you have to do a fast recloser and then a switch on to fault. This is a real example where we see a 2 break per phase breaker, because we have for phase R 2 main contacts, for phase S 2 main contacts, for phase T 2 main contacts. Then we have 3 open coils, 1 per each phase. So open coil 1, open coil 2, open coil 3, and then the closed coil. If you see the timeline here, we start from 0 and all the operations finish more or less 370 milliseconds later. This is a confirm that this is the typical result that you may expect when you do a reclosing cycle testing. Some highlights on the time that you are going to measure. So you can see that between the close command and the open command, the time is 55 milliseconds. And this must be respected, because if you try to issue in the same time an open command and a close command, in order that for the circuit breaker not to be confused, because if you tell to the circuit breaker to open and in the same time to close, then can be confused. So there is a device, there is a mechanism inside that keeps separated the close command from the open command, even if the 2 commands are overlapped. So as we already said many times, once the breaker is closed and then you need to open immediately after, then this time must be very, very short. In this case is 22 milliseconds. And the time that the main contacts remain closed within a switch on to fault operation is called dwell time. And once again, we must be aware that the time from the time that the circuit breaker needs to do all the operations is always very short. We can see here that from the close command, from the close command to the final open position of the main contacts, the time is 78 milliseconds, and it is definitely a very short time. CBA 3000 gives you a very straightforward way to choose the sequence of the operation to be executed. So there is a button, you press it, then you select here the sequence that you want to do. Can be a normal or a single close, single open operation, but also a close to open to close, close open, and so on. So you press cell, you select the sequence, you press start, and then your results is on the screen. I think it's time now for the second poll. So, yeah. Please answer to the question. Andrei, are you there?
Yes, I'm here.
Okay, I'm not checking the
No, I'm checking, and I see there is a fight. There is a big fight. There is 51 correct answers, 43 not correct answers, and 7 absolutely not correct answers. I see 57% people have voted. What we meant by this number is what is the direct value we measure in order to understand time. So what do we first measure to understand what is the opening and the closing time? Yes, in the end, we do get time, but before that, we measure something else to understand what is the time. So we have 62% of people voted. I might have given you some idea, but for now, let's wait a little bit, and maybe Simone, are you okay? Maybe just to take a short answer to 1 or 2 questions, or would you like to do that in the end?
Let's do in the end.
In the end, okay.
Okay.
So, okay, good. So we have 66% of people voted. I'm closing the votes in 5, 4, 3, 2, 1. Close poll, and the correct answer is resistance, which is C. We measure resistance in order to measure time. As Simona explained, you have infinite resistance when the circuit breaker is open and almost zero resistance when the circuit breaker is closed. So by injecting voltage and measuring current, we measure resistance, and thus we measure time. So congratulations to the 52% of the people who have got a correct question. And now we can continue. Simone, feel free to continue, please.
Okay, thanks. Having understood that the open and close time are parameter very important, now we understand another very important parameter, that is the resistance of the contact. So we said before that the resistance has a very low value in the range of microohms. But why is necessary that the resistance has a very low value? And the answer is here. You can see a typical load current. Let's take an easy number like 100 amp that flow into a resistor of 100 micro ohms. Thanks to the power calculation formula, that is resistance multiplied by the square of the current, you get 1 watt. So it's a very, very small power that is dissipated on this resistor. But let's change the order of magnitude. So we switch from microohms to milliohms, and we see that we are going from 1 watt to 1000 of watt. And we know that the hair dryer or the oven that we have in our houses has a power like this, and we know how much heat they can produce. So it's very important to keep under control the resistance to avoid situation like this. So in this picture, you see that there is one contact here. In this case, it's not a main contact, but the concept is the same. Here is a piece of metal that is probably not touching very well the other part of the asset. This creates a higher resistance, then it creates this kind of situation. So this part is much more hot than the other two, and the heat, if remain for a long time, can damage the asset, can manage the conductor, because increase the speed of the aging of the asset. But Albert now is here to remind us that the power itself is not producing heat. What is producing heat is the energy dissipated. So we have to multiply the power by the time, because the power can be very high, but if it is applied for 0 time, then there is no heat dissipated. But what is important to keep in mind is that higher is the resistance, smaller is the time to reach a very high temperature. How to measure a resistance? So seems a very easy job, because if you take a multimeter, a good multimeter can measure a resistance in a very fast and easy way. So you take 2 wires, you connect to the multimeter, you select the function to measure resistances, and then you get a value. But this method is called 2-wire method. The name is 2-wire because only 2 wires are used to measure this resistance. But there is a problem with this method. So look this yellow square. This represents the multimeter. So in order to measure the resistance, the multimeter will apply a very small current that is going out from these 2 plugs. This current will flow into the resistance, but also into the 2 wires, of course. And the only way to measure the resistance is also to measure the voltage. And the place where the multimeter measures the voltage is the terminals. So in conclusion, if you do a measurement like this, you are not only measuring the resistance of your contacts, but you're also measuring the resistance of the 2 wires. And we can see from this formula that the total resistance is the contact resistance plus the resistance of the 2 wires. So even if you compensate this value, because you can say, if I know before, I can subtract. Yes, this is true, but it's very difficult to apply this compensation, because this cable is difficult, that is well measured. So, but what is important to say is that is the principle itself that is not so safe. I really need a solution to avoid to add extra resistances in my measurement. And the solution is the 4-wire method. What we do is to split in 2 the measurement device. You need the current source and the voltage input into different devices. Since the number of devices now is 2, then the number of wires become 4, and you can see cable number 1, cable number 2, cable 3, and cable 4. With this indication, we can also see in the scheme that this is the cable number 1, the cable number 2, cable number 3, and cable number 4. With this measurement setup, what we are doing is to measure the voltage only on the resistance, on the contact resistance itself. I'm not measuring the resistance of these 2 wires. Why? Because there is no current flow in this branch, because any voltage input is a very high impedance, so the current cannot flow in this wire. So in trying to explain it with other words, the 4-wire method is more reliable because in principle it avoids to measure extra resistances that are not required. But the 4-wire method itself alone does not always guarantee to get the most correct value, because when you need to measure a very low resistance in the range of micro ohms, you need to take some precautions. First of all, the place you put the voltage terminal must be right. If you make a mistake in the positioning of this terminal, then you get a wrong value. Then you need to inject a current with high amplitude. Then the current amplitude must be very stable. This means you need a DC current. And also you need a very good noise rejection. Now we are going to explain one by one in details. Imagine to take a copper bar. The resistance of a copper bar depends on a very simple formula, that is this. So you take the copper resistivity, you multiply by the length, and you divide by the section. So from here you see that longer is the copper bar, less is the resistance, so higher is the resistance, higher is the section, less is the resistance. Trying to give you some numbers, you can see here that the copper resistivity is 0.017 with this unit that I'm not going to read. I'm taking a length of 0.5 meters and a section of 300 millimeters square. Applying, putting this number in the formula, we get a resistance value of 28 micro ohms. That, for our purposes, is a reasonable value. But you can imagine that the copper bar can be divided in smaller pieces of copper bars connected in series. For example, we can think to divide the copper bar in 4. I decided to divide it in 4 for the sake of simplicity, but you can imagine this number can be any number. You can divide in an infinite number of pieces, but let's keep 4 for simplicity. So the total resistance of 28 micro ohms comes from the sum of 4 small resistances, each one with its own value. So if I place the voltage terminal at the very end of the copper bar, is like to say that I'm measuring the series of these 4 small pieces. So the value that I get is 28 micro ohms. But if I change the position of the terminals, for example, I put one here and one here, So I'm saying that I'm measuring only 2 out of 4 pieces of resistance. And then the final result is 14 micro ohms. This must be very well understood because when you are in substation, you can easily make such kind of mistake. You can have a look. This is the current wire, and this is the voltage terminal. You can see that if you place the voltage terminal here, you can get a result of 106 micro ohms. But if you move the terminal from this position to this position that as a first glance seems to be the same, but actually is not, and you can see how big is the error that you are doing if you are not putting the terminal here, because the surface contact of these two metal plates create this high resistance. So please be very pay very much attention on where you place the voltage terminal. When we discuss about medium voltage circuit breaker, you may have the same issue. Let's take a medium voltage circuit breaker like this, in the version that you can remove from the cell. Sorry, there was another chat here. Close. Okay. So imagine that you have to apply your terminal here. So you have to choose carefully where to place the terminal. So in order to do not make mistakes or do not have doubts, special adapters may be required for a proper connection. There is another type of medium voltage circuit breaker. This is the opposite. This type of breaker is the type that you cannot remove from the cell, but the concept of to place the clamps and the terminal in the right position remain valid. So this is a picture where you can see an example, a real example. The test current must have a high amplitude, and now we see why. Imagine to inject only 10 amp. What you get is a value of voltage that is 280 microvolts. And believe me, it's very difficult to measure such low value when you are in substation. But in general, this is a difficult value to be measured with high accuracy. So why not to increase this value by injecting a higher current? And the recommended test current is 100 amp. If we inject 100 amp, then we get 2.8 millivolt, and this is definitely a much easier value to be measured with high accuracy. Albert is coming here again to highlight something that maybe you don't know. Every time you touch with your clamp a piece of metal, what you are going to create is a kind of thermocouple. So those two different metals, when they touch each other, generate itself some microvolts. And this is how a thermocouple works. And these microvolts also depend on temperature. And this has a name, this effect is called Seebeck effect. So why I'm telling you this? Because since we are looking for very small value in terms of resistances, and we want a very high accuracy, this microvolt may affect the measurement and reduce the accuracy. So every micro ohm meter must compensate this extra voltage in the beginning. So this voltage is a kind of offset that must be compensated. And now we understand why it's better to have a pure DC current instead of a rectified current. Because if you are in such a situation, you are not interested in what is the voltage peak, but you are interested in only the DC component, and the DC component must be calculated from this waveform. So what your measuring device can do is an approximation, because it's applying mathematical formulas to calculate the DC component. Another inaccuracy can be due to the fact that the peak voltage is much higher than the DC component. So you are going to select a range in your, let's say, multimeter or voltmeter in order to measure this peak that is too high, and then you are not able in the end to be accurate for the measurement of very small voltage that in the end is the DC component, that will be small for sure. So better to have DC current to avoid these possible inaccuracies. In the end, you really need a very good noise rejection. Imagine to measure a contact resistance of this breaker in such a situation with a live bus bar around you. So imagine to measure 1 millivolt in such a situation. It is very difficult. You need to take precautions. For example, your micrometer needs shielded cables and also filters of signal that comes from the busbar that are induced in the cable, and these signals are typically at the frequency of the line. So the current source and the voltage input are present into the CBA 3000. So this is the voltage source. These are the voltage input. And you see we are applying a scheme, connection scheme, that implement the 4-wire method. So this is the current generator, and this is the voltage input here. So 1, 2, 3, 4 wires. And this is an example for the 2 break per phase breakers. So 1 current generator that inject the current in the 2 chambers, and then we apply 2 voltage input here. And thanks to this, we can measure in the same time up to 6 resistances. So this was the measurement of the static contact resistance. Now we are going to explain how to measure the dynamic contact resistance. And we understand what are the information that we get from this measurement. This is a picture that we already saw before, but here is necessary to for better understanding, to repeat this, to discuss in front of this picture once again. So this is the main contact. So when this part touch this is creating the main contact. And when this part touch this is creating the arching contact. So how to measure? First of all, you inject the current in the main contact. Then you issue the open command, so the main contact start to move. You keep the current until the main contact is fully open, but also you have to record the current variations with at least 10 kilohertz as a sample frequency, because you need a quite good time resolution. Otherwise, you are not able to see a proper profile of your dynamic resistance. Must be underlined that you don't need a different setup. The setup that we discussed before is the same, can be used also for the dynamic resistance. In the end, we are measuring resistances, so the setup must be the same. So this is a real measurement in the field that we took time ago. So this represents the value when the main contact is still closed. Then the main contact start to move. So here the main contact is now open, but the arcing contact is still closed. And you see that we go from the range of micro ohms to some millivolt. So at least you see that the value of the arcing contact is higher than the main contact. And in the end, when also the arcing contact is open, the resistance go to a very high value. So this plateau is because we cannot plot infinity. So in order to have a graph, you just clip the graph at this point, and we draw a line like this. But this is there only for the sake of the good drawing. It's not possible to plot infinity. What are the information that we can get from this test? For example, is the value of the arcing contact. In this case, the average value is 5 millivolt. And when the arcing contact start to be damaged, this value may increase. But not only the average value, also the part that is burned reduce his conductivity. This means increase the resistivity. So from a situation like this, we can notice a shorter time. For example, this is a possible result of an arcing contact that is a little bit burned on its surface. So it's important to measure the length and the average value of the arcing contact because, as we said before, is that part of the contact that absorb the arc. So once the resistivity of this component is not so good, is not able anymore to absorb the energy in the proper way. And I repeat once again, every time the fault current is interrupted, the main contact does not suffer so much, but the arcing contact, yes, it suffers. And then after a few fault current interruption is absolutely necessary to perform at least one dynamic contact resistance measurement. And if the equivalent length is less than the recommended value that the manufacturer is providing, you need to repair. I'm talking about length, but we don't see here millimeters, but we see milliseconds. In order to have this length, not in time, but in millimeters, we need to apply a movement transducer that give the information of the distance that the main contact is doing during the movement, but this will be explained later on. This quite nice graph comes from an open operation. So if you want to verify with, let's say, high accuracy the arcing contact, we recommend to do it during opening operation, because if you try to do it during the closing operation, the graph is not so nice, mainly for two reasons. The speed of the contact is higher because the contacts are open, they start to move, and when they touch each other, the acceleration the acceleration make the speed to be higher at the end. So this goes to introduce vibrations also. Another aspect is that you are going from a very low very low current value because the contact is open. So ideally the current is 0 because the the contact is open. When it start to touch each other, so the current start to flow, this current step may also produce this kind of disturbs. So long story short, if you want to analyze your main contact and your arcing contact, please do it while you are doing an opening operation. This is a measurement that one of my customers shared with me. I went to do a training. I teach to them the concept of the dynamic resistance and what are the information that you can get from them. Then they did the test and they found bounces when the contact, the phase B in this case, were closed. So thanks to the possibility to do a dynamic resistance, they got the confirmation that this was not a mistake of the timing input of the device, but this was a real behavior. This is for example, the dynamic resistance when it was closing. So imagine that this comes from infinity going down, and then there is a rise of the resistance, and then back to a low value. So the dynamic resistance gave, in this case, the confirmation that bounces were real. This screen is a screen that comes from the breaker analyzer called CB8000. Is also a device that you can use for your test. So CB8000 is one of our best seller device. Is on the market since many years. So you can decide to use CB3000 or CB8000, but of course CB8000 is much more advanced. Okay, so we now discuss about the possibility to understand if the mechanisms and leverages that transfer the movement to the main contact are working good or not. And this section is called motion analysis. So the first tool that you need is to find the proper transducer. There are two types mainly. So the rotary transducer and the linear transducer. So what you have to do is to find a way to connect this transducer to the actual leverages, to the mechanical arms, in order to move this slider together with the leverages. So can be linear, so this part slides along this line, or can be rotary, because the mechanism can also be rotary. So not necessarily you have to imagine a piece of iron that moves back and forth. The transducer, we can see the transducer as a variable resistor. So what we are going to measure is a voltage that change when the position of this cursor change. Since this cursor is connected to the breaker, the movement of this will tell me something about the movement of the breaker. We are measuring voltage, so what we are going to do is to find a correlation that is telling me for every variation of voltage how many millimeters of variation it means. So we are not going to understand everything about this. It's not complex, but not necessary that we go in details now. What you need is to provide a voltage to the transducer, because remember, it is a resistor. You have to say how long is the transducer. Then you have to say how much is the distance that you expect that the leverage is doing. Then you have to decide if you are going to do an open command, or open operation, or a close operation. In the end, what you see here is the actual movement in terms of stroke, where stroke is this distance. So once you place the transducer and you get your correct mechanical coupling, what you are going to do is to measure also the speed of the mechanisms, because I repeat once again, the speed is very important, because this speed has a direct impact on the opening and close time of your breaker. So how to measure the speed? The speed is a very simple concept. You take 2 points on the space, and the time that you need to go from point A to point B makes the speed. So space divided by time. Actually is exactly the same principle of the speed check that police use to understand how fast we are going with our car. Okay, Albert, want to say something about space-time? Is an interesting topic, but I think not for today. Now we have to understand how, where to place those 2 points. This is a graph, a real graph, that is telling us what type of movement the breaker is doing after an opening command, because this indication is telling me that the circuit breaker was closed, and from this point is open. So you can decide to place those 2 datum points where you want. So let's define this as an independent datum points, or you can fix the position of the datum point A at the transition, where it goes from close to open, but can be also from open to close. And the second is placed after a predefined time offset. So for example, you can say, I wanted to measure the speed always using a point that comes 20 milliseconds after the transition close to open, just to have a possibility to place a datum point applying always the same condition in order to have results that you can compare. Another possibility is to, instead of decide a time offset, you can decide to apply a distance offset. For example, can be a percentage of the total stroke of the circuit breaker. Actually, this is the most used. The point B can be, for example, placed at the 25% of the total stroke, or the 75% of the total stroke. It's up to the operator or to the regulations that must be respected. This is another real example. So we have 3 main contacts here, phase A, B, and C. But I decided to put in this picture only the graph that belongs to the transducer connected to the phase A, And this is the dynamic resistance of the contact of the phase A. So we can understand from here that the phase A switched from the closed to open position in this point that correspond to this line here. And these two points are the representation of the two datum points that were set in the breaker analyzer. We can see that this point correspond to the transition close to open of the phase A. The second, most probably, were decided as an offset of distance from this point. There are a lot of information that you can extract from emotional analysis. We cannot discuss everything today because we are already quite late in our schedule, but this will help you to start to say understand where at least to look and to be informed. In the web you can find a lot of information around this. There are books, papers. Feel free to read all of them. So just to say that we are not going to explore every single detail of what is possible to understand from this kind of analysis. Just two information that I can give you. We can understand the main contact wipe. So you can see this plateau means that the main contact is still not moving, and exactly in this moment start to move. So from this point to this point is the distance that the two parts that are going to compose the main contact are overlapping and sliding one over the other. And this, if we look at this graph, we see that the contact wipe is 58, more or less 59 millimeters. And finally, here we can see that from the graph, if we compare the transducer graph with the dynamic resistance graph, we can finally see that the arcing contact can be seen as can be expressed in millimeters. In this case, is 25. We can also understand what is the total stroke. So if we take the position at the beginning and the position when the mechanisms reach the steady state, this is telling us what is the total stroke of the circuit breaker. These 2 points are the datum points. So thanks to this, we can measure the speed. This is an over travel. So you can imagine the main contact that is open, then you close. When they touch each other, there is a moment where the arm compress the other. Then you can see that you go a little bit beyond the steady state. Then you have a rebound, maybe more than one, and the end you wait the steady state. This information are important because if the over travel is too much and also the rebound is too much, and maybe you can see oscillation here, this is a clear indication that something is going wrong inside your mechanisms. This table is a resume of possible value that you can get from this kind of analysis using the software of a breaker analyzer. Now some interesting pictures that give you an idea on what you need to do when you are in the field. So in this example, we are placing a rotary transducer that is this, but we need to, so we cannot place the transducer directly on the mechanisms here. So we need to put a shaft and also a damper, because this is a kind of shock absorber, because you cannot connect directly the rotary transducer to the shaft, otherwise you can damage the transducer. So you need this kind of damper in the middle. I need to also highlight that every circuit breaker is different from another. So this is an example. So this is how we connect the transducer in this particular model. But if you change model, maybe the shaft that you need is different. Maybe you don't need a shaft, you need something else. So what you really need to pay attention in the beginning is to do a survey. What is the type of breaker that you are going to test, and understand if the mechanical coupling, if you are able to do it, or if you need something. For example, you don't have the shaft because simply you don't have it and you have to find. So long story short, before to do a motion analysis, please verify that the mechanical coupling is possible to be executed. Okay, now once the transducer is placed, maybe you need some fine adjustment, and then in the end you can lock the transducer through this kind of flexible shaft. Once the transducer is well placed, well mounted, and you are sure that if the breaker moves and the movement is well transferred to this, I mean, if you open and close the breaker and you see vibrations in the transducer, this means that it's not well placed. So you are going to measure the vibration of the transducer instead of possible mistakes, possible defects in the breaker. So the positioning and the mechanical coupling on the transducer is extremely important to avoid confusions. You don't have to see graphs distorted that depends only from a bad mechanical coupling of the transducer. I think now is time for another survey. Let me see. Yes, and I start, sorry, the polls, not the survey. Please answer to the questions, and then we can proceed with the final discussion of this webinar. Andrei, how is going? Andrei, are you there? Seems not. Okay, I see that the 75% of you, now 76, 78.
Sorry, Simone, I'm here. I just didn't know how to unmute. So, but please do continue. I also see that people are much more accurate when it comes to this this question.
Okay.
I see also a lot of questions, but there are only 4 or 5 which have not been answered. So when we are done, you can maybe focus on those 4 or 5.
Okay.
And guys, just to let you know, we will definitely extend for at least 15 minutes, maybe even 20 this webinar, since we see there is a lot of interest, and Simone is trying to go as much as possible in details to explain the concepts.
Okay, I think we can close the poll.
Okay. Are you going to announce the winner and the result?
Yes. So the winner is answer number A with the 72%.
So
and it is the correct one. Yes.
Perfect.
Okay. So 3, 2, 1, close.
Perfect.
Okay. The next argument is how to test a circuit breaker keeping the safety condition. The safety condition are represented by the connection to the ground of the two sides of the circuit breaker. So it's quite everybody knows that the ground connection is there to avoid extra voltages in order to protect the operator in substations. So substation is a place where you have to really pay attention to the voltages. So whenever you put out of service the breaker, then you need to connect the two sides to the ground. These are examples of ground leads. This is one example, and this is a second example. We understood before that the most typical way to understand if a contact is closed or open is to measure resistance. And we said before that typically we go from a very small resistance when the circuit breaker is closed to infinity when it is open. But now we understand that in order to have this situation, you need to remove one of the two sides from the ground. So what you are doing is actually breaking one rules. Actually, you cannot do this, but this is something that if you don't have a proper device able to measure the timing when the two sides are grounded, the only option is to remove one of the two ground leads. So we see now the difference. So we are not going from a small value to infinity, but we are going from a small value to another small value. So you need a device able to understand this small difference. Why? Because when you connect the two ground leads, what you are doing is to connect in parallel to the contact another resistor that is represented by the ground leads and the ground grid. To give you some ideas, the contact resistance is in the range of tens of microohms. The ground resistance is in the range of hundreds of milliohms. And when the circuit breaker is closed, these two resistance are in parallel. But since this is much smaller than this, in the end, when the circuit breaker is closed, what you get is again the contact resistance. So if you use a traditional method, the traditional method will not be accurate in order to understand this this small variation. So what you need is to find an advanced method. The advanced method means inject current into the breaker, do the operation, so open and close, and look for variations. So the variation in current and voltage. So you see, when the circuit breaker is still closed, the current is flowing. In this case, in this example, is 130 amp. Then it opens, so the resistance increases because the current will flow only in the ground. So there is a current drop. Then you close again, then the current can return to higher value. So if I'm able to detect this variation, I'm able to perform the time measurement. Okay, this is more or less the same picture as before. Circuit breaker closed, circuit breaker open, circuit breaker closed. This is the variation of the current, and this is the variation of the voltage. Okay, but those graphs were ideal graph. These are simulations in laboratory, just to clarify the concept. So this is what we are looking for, these kind of variations. But when you do the test in the field, you will not get these ideal graphs. You will get something like this, because you have the line frequency that is coupling, and you see a 50 or 60 hertz that is superimposed to your signals, for example. When you do the measurement, you really need something that filter out these extra signal that are going to reduce the time accuracy, because if this step is not very fast, for example, due to a superimposed signal, this is not so fast, then the immediate effect is that your time measurement will be not accurate. So you really need to take precautions when you take this signal in order to measure the time. And this is another reason that explains that the current generator that you are using must have a very stable amplitude, must be extremely flat, because if the generator introduce itself variations, then it will become difficult to be accurate in terms of time measurement. I forgot to highlight this also before when we were discussing about dynamic resistance. Without a very flat DC source, what you get in the end is something that can affect. So you can see variations that does not belongs to the arcing contact or the main contact, but depends from the not good stability of the current source. So what we said is that we are looking for small variation of resistances. So what you need is to use the same setup that you are using for static and dynamic contact resistance, and the same setup can be used also for time measurement. In conclusion, with a single setup, you do everything: timing, static resistance, and also contact resistance. This is the advantage to do the test in both sides grounded mode. And now we comes to discuss about GIS circuit breaker. After this long discussion, we are now ready to understand that the circuit breaker that are gas insulated in the end are always must be tested with the same principle of the both sides grounded of the air insulated circuit breaker, because GIS circuit breaker always have earth disconnector at the two sides of the main contact that are connecting this to the ground. So we are again in the same situation. GIS circuit breaker are always both sides grounded. The only problem with GIS is that the ground resistance is not in the range of hundreds of milliohms. In this case, is hundreds of microohms. This is the problem here. So your breaker analyzer must be even more accurate, because the variation that we are looking for now is much smaller. So in this table, I try to resume this concept. So we are going from microohms to 100 of milliohms. And this is a quite large variation, but in this case, the variation is very small. Just to say, GIS breaker does not the method to test the timing test of GIS breaker does not introduce new concepts. Once you learn the concept of the both sides grounded, you already learned about how to test GIS breakers. But the GIS breakers introduce one difficulty, that is the connection. If you want to connect a clamp, you really have to find the proper position where to place it. And not in all GIS breaker you find a comfortable place where position where to connect this clamp. This is an example. You can see in this case we try to use a quite standard clamp. You see from the picture here that the contact is let's say quite good, but maybe not the best. So when you operate the circuit breaker, the vibrations of the movement may reflect in the vibration of the clamp. So if it's not well connected, the vibration of the clamps may result, you can see in the picture, in false bounces, because for a very, very short time, the current is not well flowing because it is not touching very well. So what we recommend is always to find a good place where to put your clamp, and if required, use special terminals that help you to do a tight connection and avoid mechanical vibrations. Okay, we are in the end of the session. Just a quick review of what we can offer to you as a solution for the test that we discussed this morning all together. So we recommend CBA 3000. So it's made by a section dedicated for the timing input. So it's made up to 24. Is divided in 3 boards. Each one is made of 8 inputs. The minimum is 1, but you can add 2 other cards. So it can be 8, can be 16, can be 24 inputs. The board can be of 2 different type. The standard one, you can use it to measure the time of main contact and auxiliary contact, and also to detect if there is a pre-insertion resistor present or not. I mean, when I say detection, I mean the detection of the presence of a PIR, a pre-insertion resistor during the movement. If you want to see the profile and the value of pre-insertion resistor, you need the advanced board. So they do the same job, but the advanced is also telling you more information about pre-insertion resistors. Then we come to the coil commands. Can be 2, but can also be 4 or 6. You are free to program each one of these to be an open or close command, and you can also assign one of these as you like to phase A, B, or C, or not defined if you have one coil that command the 3 phase together. And we can measure coil current with peaks up to 60 amp. Then we have analog inputs. Each one of these, again, you are free to program as you like. Each one of these can be a generic analog input, can be used for micrometer measurement, or to get a signal from treble transducers, from current clamps, and why not also from pressure transducers. This is to verify the trend of the gas pressures during the operation of your circuit breaker. DC generators can be 0, can be 1, can be 3. But the only way to be able to test GIS breakers or air insulated breakers in both sides ground mode, you need to have 3 generators. Then the software is designed in order to help the user to do the job in the most convenient way. So there is the instrument settings, because it's a programmable device, so you have to choose the right settings for your test. Then you decide a test sequence you can save and execute in a row. In the end, there is a test and result section where you can see the final result of your test. So this is a device that is able to do many functions, but we have some predefined configurations that is preparing for the user the hardware in the right way. So just answer to a few questions, tell to the instrument how many breaks the circuit breaker has, how many open coil, how many closed coil, if you're using micrometers, if you are using, you want to use the both sides grounded method, yes or no, if you want to see the pre-insertion resistor profiles, and if you are doing motion analysis. Just answer to this, and the CBA 3000 will be immediately after set up for you. Every predefined configuration brings also a schematic. So if you press the help button, you see every input, what is the functions, and where must be connected to. This is very useful in the field, because you just press that question mark and you see immediately what are the wiring that you have to do. Not only predefined configuration, if you go to the advanced and custom section, then you are free to adjust as you like every single input and output of the device. Then test plan editor, you put in a sequence all the operations you want to do. In this case, for example, you want to start with an open, then a close open, dynamic resistance, and the static resistance, but you can prepare your list as you want. In the end, you see all the result in the screen in a graphical form and also in a numerical form. Okay, I think it's time to close the session, because all the argument has been presented. So, Andrei, now we can read some questions and give some answers.
Sure. So I don't know if you can see all the questions.
Let me open the dashboard.
Please.
Questions.
Look, in the meantime, while you're checking the questions, can I launch the last poll and you read the questions? Is that okay?
Yes. Yes.
Okay. So, guys and girls, I'm going to launch the last poll, and I'm waiting for you to reply. In the meantime, Simone is checking the questions which have not been answered. So the question is, both sides grounded option is helpful because A, it removes the effect, I'm sorry, that was wrong spelling, the effect of induction, and there is no need to unground. B, the measurement is much more accurate, or C, no need to connect command signal. So what is the correct answer? Okay, 20% of the people have voted, but I see that one of the answers, which is not the correct one, is gaining more popularity. Almost 50% of the people have voted, and now we are getting better. So Simone was discussing the benefits of both sides grounded, and what would be the biggest benefit of both sides grounded. There are a few of them, but you can take a look and think about it. We still have about 30 seconds. 55% of the people have voted. Now we are at 49 versus 50. Let's give it 15 more seconds. And let's go with 5, 4, 3, 2, 1, and we close the poll. And we close the poll at the exact moment. So the correct answer is removes the effects of induction, and there is no need to unground. That is the biggest advantage. When we talk about accuracy, it could be a little bit more accurate, but not a lot. So accuracy is more or less the same if we measure in the standard way or with both sides grounded. So that's the 49 and 1%, no need to connect command signal. We do need to connect command signal in both cases. So now, Simone, if you're ready, you can answer some of the questions.
I see a lot of questions. Let me expand.
Expand, and there is one question from Mr. Mebin Matthew, which came at 10:26, which I haven't replied. Do you see that one?
Which name, sorry?
Matthew Mebin. It came at 10:26.
10:26. Okay.
So we can first read it out loud for everybody to hear.
How much is acceptable speed of auxiliary contact changeover? We can see in the previous slides, the open auxiliary is received, still closed auxiliary as